let us begin. Now, harmonics, right? So we start module two, right? Well, module two is mostly all about waves, right? So where it causes us to start is in harmonics. Now, harmonics have to speak about different frequencies of waves specifically, and we're going to be looking at all these terminologies surrounding harmonics. And then within the scope of the CAPE Unit 1 syllabus, we're going to be focusing on simple harmonics, right? But because the section is called harmonics, right, I started there. So what does harmonics really encompass in physics, right? As I said, right, it refers to varying frequencies, right, within a system, right? So a system can oscillate, right? And we're gonna look at what that oscillation means really and truly, right? And when a system undergoes this type of oscillation, it vibrates at different modes or frequencies. The one that's a fundamental frequency and its harmonics, right? So for example, on the right hand side of the screen, I show the vibrating of 6 different strings, right? Showing the fundamental harmonic, then second, third, the fourth, the fifth, the sixth. Now, describing harmonics requires a fair bit of a grasp of math, right? But we won't get into really higher order harmonics or in types of, well, we're going to be discussing fundamental frequencies when we speak about the actual applications of harmonics in the real world. Well, yeah, in the real world, right? But we're gonna not going to be looking at second harmonics or the third harmonic or the whatever harmonic, right? We're just going to be looking at really and truly what is an oscillation and only look at harmonics in a simple system. And that's where we come to the concept of simple harmonics, right? So we're trying to describe the motion, right, in a simple harmonic system, right? So simple harmonic motion really and truly is a specific type of oscillatory motion where the restoring force, right, in the system is directly proportional to the displacement from the equilibrium position and acts opposite, right, to the direction, right, of the oscillation. So we're going to be speaking about those type of stuff. Okay, so the question is each harmonic increasing by half lambda? Um in what context though? Mm-hmm. Mm-hmm. Yeah. All right, so it's half, then a third, then a quarter, then a fifth, then a sixth, but we're not gonna go too deep into that. All right, it's just to introduce harmonics in and of itself. All right, so lovely. So harmonic motion, we're looking at oscillatory patterns, right? So for example, we can see the oscillation of a spring here, right? And oscillations really speak to that circular pattern. And when we talk about that, we're going to be using what we call circular functions to describe oscillations, right? Circular functions are sometimes called trigonometric functions, right? So we're going to be using those to describe the motions of these objects. So as we see the spring going down, then up as it extends and then contracts, we can actually see a circular motion coming out of that. So no matter whether it be a spring or whether it be the movement of a bob on a pendulum, right, they all come back to this circular oscillatory motion that I need to describe to you guys first before we start speaking about other forms of harmonic motion and going into the derivations, right, that we need for the kinematics of these systems, right? But everybody more or less understands the concept of an oscillatory motion, right? Danielle? Welcome, Danielle. Just saying that I never said welcome. And the person named S. Okay. All right, so we understand the concept of the motion. Now, for simple harmonics to occur, or simple harmonic motion to occur, there are different factors. Firstly, we need to have a specific type of oscillation, right? So we need to define really and truly what oscillations mean for simple harmonics, right? And then speak about the time t, well, the time period, right? And the restoring force. So firstly, an oscillation is said to be simple harmonic motion when the acceleration is proportional to the displacement. That's one condition there. So the acceleration is proportional to the displacement. We're going to be looking at acceleration and displacement equations, and we can mathematically describe that relationship, right? The acceleration also is in the opposite direction to the displacement. And we're going to be looking at the vector diagrams there, right? Just for a little preview of that though, if we have the spring descending, we're gonna always have some amount of acceleration opposite to its motion, right? So as the spring is descending, the acceleration is actually going up. And as the spring is actually extending down, the acceleration, well, as the spring is going up, then the acceleration is down. So the acceleration always opposes the motion or the displacement specifically, right? The period t, in this case as well, the objects swinging are periodic. So it's meaning that they are repeated in regular intervals according to their frequency and time period, right? So if an object swings freely, it always takes the same time, right? So time should have been there, right? So the period should be more or less the same. So it must be regular intervals. If this is not met, the system is not in simple harmonic motion. If the acceleration is not opposite to the direction of displacement, it is not simple harmonic motion. And of course, if the acceleration is not proportional to the displacement, then it is not simple harmonic motion, right? And then the restoring force specifically, now, when an object is moving in simple harmonic motion, a force called the restoring force F, right? In newtons, of course, is always trying to return the object to its equilibrium position, right? So you're going to be looking at the restoring force there, right? And the direction of the restoring force will always be the direction of the acceleration, as Newton's second law gives us force is equal to mass times acceleration. So we should remember that F is equal to ma, right? They are both vectors. So whatever direction the restoring force is in, that would be the same direction as the acceleration. So when we say that the acceleration is opposing the direction of displacement, that simply means that there's a restoring force, right? Because restoring forces are oppositional forces, as discussed in module 1, right? So let's have a look at the rest of the concepts. Are there any questions or concerns? All right, no? Any issues? All right, okay. So let's have a look at this. So a simple pendulum lab. So hopefully we are able to actually see what's happening here, right? So the swinging of a simple pendulum is seen as somewhat harmonic, right? So looking at the simple harmonics of this system, right? So it would have the same period, right, through and through. There are regular intervals of this oscillatory movement, right? And there will be, right, an acceleration that opposes the displacement, right? But from here we can get a few concepts, right? From here we want to have a few concepts. While the pendulum is resting, this is what we call the equilibrium position, right? So we call this the equilibrium position. And if I were to drag the pendulum at some degree, as we can see at the top of the simulation, right, to 20 degrees, right, that will be an arc length. From circular motion, we know that to be the angular displacement, right? So we have displaced the bob at 20 degrees there, right? So that's the angular displacement. The distance between where the bob is now and the dotted line, the equilibrium line, right? That is what we call the the amplitude or the displacement, right? Now I'm going to use amplitude and displacement interchangeably, but note that they are not the same, right? There's a distinct difference that we're going to be looking at as we go further, right? So we know that this is when the bob is at equilibrium position where x is 0. There's no displacement from equilibrium, right? But x changes when we move from equilibrium in either the positive direction or the negative direction, right? So we have that there. So this simulation here is just to have a look at some concepts and then to actually gauge some important characteristics of simple harmonic motion. We also stated that simple harmonic motion occurs when the acceleration is opposite to the direction of oscillation or to the displacement. So if I were to displace this 20 degrees to the right, we can see that the acceleration is moving to the left. And the acceleration will increase proportionally to the displacement. And that is exactly the condition for simple harmonic motion, right? If we were to displace the object now to the left, the acceleration opposes the motion and opposes the motion and the displacement as it moves towards the right. Is this clear to everyone? So that is why the object swing in this motion as the acceleration brings it back to equilibrium. So we have an object trying to restore its equilibrium, and that's how we get simple harmonic motions. That's why things swing in this repeated pattern, right? So we look at that. So as long as we're looking at that and we're understanding that, that is very important. I know that you guys have done pendulum labs as well, so we know that the length of the string will affect the not the frequency, but the period and stuff like that, right? But we're here to understand the concept, so that should be fine. The velocity as well, we know that acceleration, right, is going to be somewhat in relation to the velocity as well, because acceleration is nothing but the first derivative of velocity. Alright, so we'll be acting in the same direction. Alrighty, so let's stop that there. So everything should be fine. That is what I'm trying to express right now. The conditions for simple harmonic motion. So spring oscillations occur in the same general way as well, right? So spring oscillations, as we can see, provides this wave here. And we're going to be looking at spring oscillations in depth throughout the PowerPoint, and we're going to be describing its period as well, right? So this is just here to show that, okay, spring oscillations are another type of oscillation, and we can look at the acceleration changes as well, all right? So here are some key terms that we need to define and we need to stick with. These are terms that we're going to be hearing for the entirety of module 2, all right? So the displacement, right, is the distance of an object from its equilibrium position, as we stated with the pendulum, right? So it's distance from the equilibrium position. The amplitude is the maximum displacement from equilibrium, right? So if I were to, where's my pen? Give me a second. Okay, so if I were to call this line, this dotted line on the screen, the equilibrium position, right? And if I were to say, let's say there's a distance x from this position, right? And then within this point here, there's a distance x1, right? So let's say that let's call this x1 and let's call this smaller distance up here x2. Let me erase that. X2, right? So x2 is a displacement, right, from the equilibrium position, right? But x1 is where we have the max displacement. The max displacement is equivalent to what we call the amplitude. So waves can be displaced, right? They can always be displaced at any amount in any period in time within its oscillation. But when it is at max displacement, that is what we call the amplitude of the wave, right? That is what we're talking about there. The angular frequency also is the rate at which the phase of the motion changes, measured in radians per second. So we're going to be looking at the angular frequency of waves and how it is different from the specific frequency, right? So angular frequency speaks to the rate at which the phase of the motion of the waves changes, and we're going to be looking at wave phases as we go through the topic. Also, the velocity is the rate of change of displacement. We know that the velocity v, well, let me just go through these right now. We know that the displacement x is a fundamental vector, right? And we know that the velocity is nothing but the first derivative of x with respect to time, right? The acceleration is nothing but the first derivative of the velocity itself, right? Or we can call the acceleration the second derivative of the displacement, right? So derivatives are used to discuss changes or to describe changes, right? So the same way in which you say velocity is a change in displacement over time, that's literally calling velocity the derivative of the displacement. So when you call something the derivative, you're speaking about the change of that thing with respect to something. All right. So remembering these things from module one, right? So the acceleration there now, the change in velocity with respect to time, or the first derivative of velocity, or we can discuss it as the second derivative of displacement. All right. The period now is the time taken for one complete oscillation, and the frequency is the number of oscillations per unit time. So these concepts will be used throughout the entirety of our stay here in Module 2. Are there any questions or concerns before we move on? Nope. Alrighty. Sure. Alrighty. So the link to Hooke's law. Now, when we speak about simple harmonic motion, we almost always think of, well, within the spring context, Hooke's law, right? F is equal to negative ky, or negative kx, or negative ke, where that k is a spring constant, and the other letter there, whether you use e, x, or y, I use x, right? That would be the displacement. Hooke's law states that for small displacements or deformations of an object, the displacement or deformation is directly proportional to the applied force or load, right? So hopefully we remember that from Hooke's law there. Alrighty. So there is a link between Hooke's law and simple harmonic motion, and we're going to be looking at that as we go through the spring oscillators, right? So I have some spring oscillator simulations in the PowerPoint, and we can discuss them. Alrighty. So let's move on. There are no issues here. Just reminding you of Hooke's law. Hooke's law is something that you'd have covered in module 1 or in CSEC. Alright. So let's look at this simulation here. I would love my vectors to be used. Alright. Alright, so let's say we add a 50-gram mass to this. Wait, hold on. What just occurred? Right. Stop. All right, so we have something like that. So just re-explaining Hooke's law here, if we have different masses, it's going to be proportional to the extension on the spring, right? So we should remember that as it relates to Hooke's law there, all right? But let's focus on a simple oscillator. Let's focus on, let's say, a 50-gram oscillator, all right? So at equilibrium, so the mass equilibrium is here, right? So displayed by that dotted line there, right? And we're gonna have a movable line here. Well, we don't need a movable line for this experiment, actually. Probably for another one in the future, but let's go. Right, so that is where the equilibrium line there, the mass equilibrium line there is, right? And if we look at the forces, for example, the acceleration acting on the spring itself, when we actually start an oscillation, right, that acceleration seeks to return, let me put it slowly, that acceleration seeks to return the mass itself to the equilibrium point, right? So we must be able, as students of physics, to describe the simple harmonic motion of not only a simple pendulum, but a mass spring system as well. So as it oscillates up and down, right, past the equilibrium point, the acceleration moves opposite to its displacement to return it to the equilibrium position, right? So we have that there. We can also look at the force on the spring as well, right, which is described generally as the restoring force. So that blue arrow there, right, would be the restoring force on the spring. And the restoring force itself, right, really is proportional to the displacement, and it can be dependent on the material of the spring. And it's the material of the spring that will give us our spring constant. Alright? So we should remember that from deformations in CSEC, but we're just revamping the information a little bit. Alright? So is this fair enough? Is this understood? We're just looking at oscillations in mass spring systems. So if everything is lovely and we can move on, just drop a 1 in the chat. If you have an issue or a question, please ask your question. All right. Just a quick question: Is the are the simulations smooth on your end, or is it choppy? I'm not sure. Let me just ask. All right, but you can understand what's happening, more or less. Okay. So we're just looking at that specifically. Now let's get into the nitty-gritty, the part that I love about physics, which is the math, of course. All right. So we'll have to look at the equations of motion. So we know that we have displacement, velocity, acceleration, right? But now we have introduced concepts like amplitude. Concepts like the angular displacement are going to be spoken about, right? The angular frequency, rather, right? So let's look at this. Simple harmonic motion arises in systems with a restoring force proportional to the displacement, as we have been driving home from the beginning, directed towards the equilibrium position. This force is described by Hooke's law, right? Remember Hooke's law, F is equal to negative kx, right? Anywhere within this derivation, if there's an issue, do ask, all right? So we're starting from Hooke's law here, right? But we also know that Newton's second law applies in this case, where F is equal to ma, right? Where a is a second derivative of the displacement, or what we call the acceleration. All right? From here, we can then equate the two, where the mass times the acceleration is equal to negative kx, right? Everything is fine there. All right, everything should be very clear here. All right, but rearranging now, right? If we get the acceleration now and add it to the spring constant divided by the mass of the system times x, we can equate everything here to 0. So what we're trying to say is take everything on the right-hand side of the equation and put it onto the left-hand side of the equation to equate everything to 0. So the next step is to equate everything to 0. All right? So the acceleration plus the spring constant divided by the mass times the displacement is equal to 0. All right? We have to know a new quantity. Omega squared is equal to k divided by m, right? What would be omega in this case? Lovely, right? So omega squared is equal to k divided by m, which is the spring constant divided by the mass of the system, right? Therefore, we can state that now the acceleration plus omega squared x is equal to 0. And we must recall that just simplifying it now, right? That the second derivative of the displacement is equal to the acceleration. So we can write it as a plus omega squared x is equal to 0, right? So then we can rearrange now to make the equation look a little bit neater, where a of t is equal to negative omega squared x of t, right? And that of t there speaks to the fact that this is dependent on time. So the acceleration within a specific point in time in the oscillation is going to be equal to negative omega squared x at a specific point in time. So if you would like to, you can simplify the equation to being a is equal to negative omega squared x. So that is the acceleration. Is that fine, everyone? So that is the derivation there for that acceleration equation. All right? Okay, no problem. If you'd like to, if you don't like the differentiation, you can always move the second derivative of displacement and put acceleration from the beginning. You can. All right? So that's what's happening here. Mm-hmm. Mm. My purpose of putting it there was to get persons used to differentiation notation, and I want persons to remember that the acceleration is linked to the velocity, and the velocity is linked to the displacement. A lot of persons tend to forget that. Mhm. So differentiation is really speaking to the change, right, in the velocity, which is a change to the second order of the displacement, really and truly. Alrighty, so we have that equation there, the first equation of motion that we have there, that describes the motion, right? And we stated that the acceleration, right, is going to be moving against the displacement, right? So from this equation also helps us to drive home the condition for simple harmonic motion. Alrighty, moving on to the next slide. Um, hopefully nobody has any issues. Hopefully everybody's okay. All right. Now we're going to be looking at the general solutions for the displacement. All right. So the general solution of the differential equation is this. All right. So x is equal to a cos omega t, or well, plus b sine omega t, right? At this level. Because once you move on to any higher levels of physics, you're going to see something called phi, which is our phase constant. But we don't speak about phase constants here. All right. So the displacement is equal to the amplitude cos the angular frequency times time, right? Or we could have b sine, right? The angular frequency times time. All right. A and B are amplitudes, right? Defined by initial conditions, right? Meaning that when you displace, when you do your actual experiment and you displace the bob for your pendulum, right? That displacement that you actually did is the max displacement, which is the amplitude. So that is set by the initial conditions of the experiment. So once you have that set, right, that is the amplitude ARB that we're defining, and omega is obviously the angular frequency, which determines the oscillation's speed, right? The angular frequency there will determine the oscillation's speed. The special case now, we can condense them now into a singular trigonometric form where x is either equal to the amplitude cos omega t or x is equal to the amplitude sine omega t, depending on initial conditions. Can anybody explain to me what initial conditions are those? Hopefully we see what is there. I don't want to look at the equations, and I want you to see what the equation is telling you. What does x equal a cos omega t mean for the oscillation? And what does the sine mean for that oscillation? Anyone? If you don't exactly know, you can let me know. Do we not know? You don't know? Okay. But if we okay, we know that cos and sine are trigonometric functions, are circular functions, right? If we were to draw something like this, right, and describe these two waves, right? We have wave 1 and we have wave 2, A and B. Which one is the sine wave and which one is the cosine wave? Anyone? The top is the sine wave, right? So let's have 0 here, let's have 1, let's have -1. We have 0 here, 1, and then -1, right? The top is the sine wave. Lovely, right? So we have that there, that sine wave there. Okay? So if we're starting from 0, the sine wave will start from 0 because the sine, right, if we were to take our calculator, the sine of 0 is 0. So the sine wave starts from the origin or the equilibrium position. So it is the same thing as if we were to draw a pendulum, right? So a pendulum at its equilibrium position like this, right? So what a sine omega t is telling us is that when the system started oscillating, it started from equilibrium. So it experienced some type of force, F, and it started oscillating from equilibrium, right? And the constraints of a sine wave is 1 and -1, as sine of 90 is 1, right? Let's look at this now. Right, it's from trigonometry. Hopefully we have our math right with us, right? What the cos wave is telling us now in B is that it starts from some max displacement, and the max displacement is the amplitude. So for the cos wave, so this is sine, right? Let me go back. I don't know why the thing skipped forward. No. Those are details that we're gonna need for the future. All right. But let's redraw now another one, right? We're looking at this displacement now, this angular displacement or this displacement now. What the cos wave is telling us is that when this oscillation started, when the object was at some amplitude A, right? So it did not start from equilibrium, and that's what I'm trying to get to you guys, right? If you see A cos omega t, it's saying that it did not start at equilibrium, and if it's saying A sine omega t, it's saying that it started at equilibrium, right? So sine speaks to the fact that it started from 0, and cos speaks to the fact that it started from some displacement other than 0. Does that make sense? That is why we use this function to describe it. Go ahead. Well, some displacement, it can be the maximum. Most times it is the maximum amplitude, right? But yeah, it can be the maximum amplitude. It can be something. It's just describing that it did not start at equilibrium. So let's keep it there so we don't build any logical or mathematical fallacies. Just saying sine start at equilibrium, cos doesn't start at equilibrium. Let's just have it at that. All right. So you should be able to look at these. Physics don't just throw mathematical equations for no reason. No, there's a reason for every single symbol. All right, it describes something. Alrighty. So the max displacement and amplitude now. So the maximum displacement are x max, or the amplitude A, represents the furthest point the oscillating object reaches from equilibrium, as we spoke about earlier. It corresponds with the maximum value of x, right? And it happens when the velocity is 0. What does that mean? X is equal to A cos omega t. X will equal to A. How did we get that there? If the velocity is 0, remember that do we remember that the angular frequency determines the speed of the wave? Do you remember this statement here? Can everybody see what I enclosed in a box there? I want everybody to read that for a second. The angular frequency determines the oscillation speed. It speaks to the speed of the oscillation, right? Therefore, if our angular frequency, if our velocity is 0, then our angular frequency is also 0. 0 times the time is going to be 0. The cos of 0 is, cos of 0 is what? Cosine of 0 is 1. Therefore, x is reduced to a times 1. Therefore, the maximum displacement or the amplitude is achieved when the speed is 0. Do we need to go over that again? All right, let's go over that. Let me see. I should be able to clear the slide without erase all the ink on the side. All right, so let's do it cleanly now, because that wasn't clean a while ago. All right, so we start off with x is equal to a cos, and it can be, well, let's do this first, right? Omega t. All right, but if the speed or the velocity is 0, go at, oh, I thought somebody raised their hands there. Right, if the speed or the velocity is 0, then we can, hold on, what's happening? Right, the speed or velocity is 0, then we can determine omega, right, to reach 0, right? That's the angular frequency. If that is 0, what will happen now? Then, comma, right, x is going to be equal to a cos 0 times t, which is 0. X is equal to a cos 0. Cosine of 0 is 1. X is equal to a times 1. X is equal to the amplitude. Does that make sense? Should make more sense now, right? So when the speed or the angular frequency is 0, the displacement, right, is maximum, or the displacement is equal to the amplitude. That is what I'm trying to get across here. Is that fine? All right, QED. All right. Give me, all right, so that should be it. Give me one moment. So let's continue now. All right, let's move on. This slide is moving a bit too fast, you know, I don't like that. Alrighty, so we're looking at this, right? The sine wave and the cos wave, right? The sine and cosine waves are very interesting, are very important, right? When it comes to discussing the oscillations, right? So we have that here. Go ahead. The last screen, okay. You can go back. All right, so there it is. All right, no problem. Hopefully everything is going swimmingly, everything is going well. All right. So Let's move on to the next slide. All right. So this is just a description of the sine curve and sine wave rather, and the cosine wave. Alrighty. We discussed that the sine. Well, this should be fine. So this is something that you've seen in trigonometry when you spoke about circular functions and the unit circle and stuff like that, right? You should have gotten that, right? And if you see in trigonometry the discussion of R functions, it is literally this discussing amplitude. An R function in math is speaking about the amplitude of a wave. So you can see that if you're doing pure math and discussing R functions, it is exactly wave functions or wave equations that they're speaking about. All right. So let's move on. So velocity in terms of the simple harmonic motion now. We looked at acceleration, we looked at displacement. Now we're going to look at velocity. Velocity is the time derivative of displacement, or what we call the first derivative of displacement with respect to time. Alrighty. If x is equal to a cos omega t, then v is equal to negative a omega sine omega t. That is the velocity there. Can everyone see that? Clearly stated, Clearly stated. So we have that equation there. Now, what does that mean? Where does that come from? Remember that velocity is the first derivative of the displacement. What do we mean by that? We mean that we differentiated in order to get this, right? Question. You don't necessarily need to understand the differentiation to bring yourself to the velocity. But do you want me to show you, yes or no? All right, so let's do the derivation then. All right, so we need to differentiate now. So if x, we're working off of this equation, x is equal to a cos omega t. All right, let me just, should I, no, I'll leave it like, well, I'll flip my screen for this so I can write on it a bit better. Everyone can still see the PowerPoint? Because sometimes when I detach my screen, it kind of gets sent out in some way. Hopefully everybody can still see, everyone can still hear. Alright, let me just check. Okay, lovely. So everything is fine. So let's get cracking at the math, right? And if you can see the smile on my face. Alright, so differentiating x is x, right, is equal to a cos omega t, right? If we need to find the velocity, right, then our velocity now, v, hopefully we can see that on the screen. Can you guys see the writing? That's interesting. See. We can't see the writing. No? What's happening here? I want to show the task, well, not show the taskbar. The velocity. Why isn't it not writing? Alright, so we've encountered our first issue. I'm not able to manipulate the PowerPoint. Give me a second. So the PowerPoint isn't moving. Alright, so one moment. I'll just reshare the PowerPoint real quick. Discard. I'll reshare the PowerPoint real quick. and then we can get into that differentiation. All right. So give me a second. Let me know when you can see the screen again. Alrighty, so everyone can see again. Yes, no, maybe. Let me check the chat. Can we see again? Okay, lovely. All right, so let me see if I can now manipulate what's on the screen now. V, okay, lovely. So V is equal to, now, if we're going to differentiate this now, right? So V is equal to the derivative of x, right? So d of dt x, right? Here. That is what we're talking about now. That x there, right? And this is equal to now the derivative dt of a cos omega t. So we're working with that, right? So we have to identify the derivative of the cosine. The derivative of cosine, let me just add that here, derivative of cosine dt, well, it would be dy technically, of the cosine omega t is going to be equal to, does anybody know that derivative? Derivative of cosine is negative sine, right? So it's negative sine omega t, right? So we end up here now, all right, so we're looking at that there. So we end up here with this function, all right? So we're trying to differentiate that. So now we have to apply the chain rule. It's a different kind of rule, right? So we have that entire function now that we already have differentiated, right, as it relates to the negative sine omega t, right? Since we have a composite function, we know what a composite function is. There's a function within a function. We have to use something that we call the chain rule, right? We have to use something that we call the chain rule. So we end up with this. dt, well, d over dt cosine of omega t, right, is equal, right? So, all right, just letting that person into the meeting, is now equal to the derivative, right, of d with respect to the function here of cosine omega t times d over dt of omega t. So what we have to realize is that because we have a cosine omega t, we have to differentiate the a cosine omega t and then differentiate again what is in the bracket of the cosine. Right? So we end up with something like that. All right. So we already know that the derivative of the cosine would give us the negative sign, right? So we end up with something interesting. We end up with this being negative sine omega t, right? And when we look here now, the derivative here of the omega t with respect to t is equal to omega. All right, so we end up with something like that. So if we put everything together now, the velocity is equal to a times the negative sign that we got, negative sine omega t, right, times omega. What is the finished expression now? V is equal to a times negative sine omega t times omega. We can simplify this to say that it is a times negative omega sine omega t right? And then we can simplify further to saying that V is equal to A, no, well, negative A omega sine omega t. And that is what we do. That's just differentiation that was required. Hold on. Move the slide technically. All right. So this is what we're looking at here. So that is how we got there. So we differentiated the overall function, then differentiated what was in the bracket, and then we multiplied them together in the chain rule there. All right, and we end up with this expression. That's how we get the omega outside here, the negative a as well, because the derivative of cosine is negative sine, therefore the a will become negative. The derivative of the omega t with respect to t is omega, and we just multiply that together. So this is negative amplitude times the angular frequency, sine the angular frequency times time there. All right, so that is how we got that equation. And it's the same thing now for the next equation, right? So that is if our entire oscillation was described by cosine. If it was described by sine, no, the derivative of sine is cosine. The derivative of cosine is negative sine. So these are the things that you just need to remember, right, about the math of this. All right, for persons doing pure math, this should be a walk in the park, right? I'm pretty sure some persons here do pure maths. Walk in the park, right? But yeah, so that is what we have here. So I don't know if you want a screenshot, because I'm gonna now erase all the ink off of the slide so I can now proceed to the regular schedule programming. All right, but that is how we got to the velocity in the first place. So no, if the displacement is described as a cos omega t, the velocity will always be negative a omega sine omega t. And if the displacement is described as a sine omega t, our velocity will always be positive a omega cos omega t. So the velocity for the cos wave, right, is going to be negative sine, right? And the velocity for the sine wave is going to be positive cos, right? So that's how it works. Any questions or concerns? I'm gonna erase the slide now, so if you need to take a screenshot or wherever, you need to do that now, because if I erase the ink, I can't just click undo. All right, so I'm gonna erase it now. But are there any questions or concerns before I do so? You can drop a 1 in the chat if everything is okay and I can move on. And if there's a question, of course, please ask the question. Can we move on? All right. Erase all the ink off the slide. All right, let's move on. So the velocity displacement relationship. So we have to look at the relationship between the velocity and the displacement, right? So from x and v expressions, so from the velocity and from the displacement expressions, we can deduce now that the velocity squared is equal to a omega squared minus omega x squared. So we have deduced this expression, right? And this is what we call the velocity displacement expression or relationship. And we can simplify that to say that v squared is equal to omega squared. All right, we just factorize the omega. We drag out the omega out of the expression, because omega is a like term across both terms. So we just factorize the omega squared, right? So it's going to be omega squared times the amplitude squared minus the displacement squared. And that is the relationship there. Now, when x is equal to 0, then the velocity, the max velocity, is now equal to the omega times the amplitude. Now, recall, we have already deduced the oscillation of a spring and the acceleration equation. We've already looked at the displacement equation, right? And we have found the maximum displacement equation, which is equal to the amplitude. Now we are looking at the velocity equation and how we calculate maximum velocity. Now, If we look at a past paper and anybody tell me that they don't know how to calculate maximum velocity, we're gonna have a personal problem, right? Because all the equations are being given. Okay, so the max velocity, right? And it is when the displacement is 0, right? Will give us omega a. But when velocity is 0, isn't xa? Isn't xa? It is. So if we're to rearrange to find now the displacement when the omega is 0, we get back the equation that we looked at before. Let's go back to that equation. The maximum equation. Well, we derived all of that. The maximum equation, right? X max is equal to a, but V max is equal to omega a. All right? Just wanted to drive home that point. Any questions or concerns before we move on? Any issues before we move on? Seems to me that everything is okay. Everything is all right. Alrighty then. Gonna give you guys a couple seconds to just take in the slide and think if you think of any questions. If you have to, just give me one moment. Alrighty. Any questions or concerns, guys? Just notice how many times I asked. So, alright, everything should be great. Should be perfect. Let's move on now. Now, period and frequency are two other concepts that we need to understand. The angular frequency omega is related to the period t and the frequency f by this equation. Well, well, frequency f through this, and it's combined with t as well, right? If we look at this equation, omega is also equal to 2 pi f. All right, so 2 pi times the frequency, and 2 pi speaks to what? Can anybody tell me where the 2 pi came from? Where did that come from? Danielle, where did that come from? The 2 pi. Sadia, let me know. Chan, where did that come from? Jamelia, what are oscillatory movements again? What is an oscillation? It's a circular movement, right? So 2 pi speaks to what? Speaks to the movement of the circle. The circumference, yes. It's the complete rotation. So the angular frequency speaks to the frequency in relation to a circle. So that's what angular frequency is in relation to regular frequency. Go ahead with this. Pi is phase difference. There, or we can speak of the phase difference in terms of pi. All right, we can. So the period is the time taken for one complete oscillation. So t is equal to the inverse of f, or 2 pi divided by the angular frequency. So there are now, we already have one equation for omega there, and we have two equations for t. And obviously, because f is in these equations, we can always transpose to find two equations for the frequency, right? Because transposition is not a problem for us here, hopefully. If not, we just need practice and then everything shall be good. All right, so the period is not only the inverse of the frequency, 1 over the frequency, but it is 2 pi divided by omega. The period of a simple pendulum is the t is equal to 2 pi square root of L over G. Right? And the period of a mass spring now is going to be t is equal to 2 pi times the square root of m over k. Therefore, we can deduce this. Alright? It can be deduced that the omega can be equal to that. Because omega squared would be it by itself. Therefore, we can know that t is also equal to 2 pi omega squared. Note, I didn't put those equations on the slides, but from the information, we must be able as physicists to analyze and to figure out whatever equation we may need. Alright? So that is that. So the derivation now, right? The derivation for this now, right? For the simple pendulum and for the mass spring pendulum, you guys don't need it on the syllabus specifically, right? But I'm not sure if anybody wants me to do a derivation for that. The derivation for that will need a diagram, but it should be really, really simple. The derivation comes from the gravitational force and the tension of a string. And then you would have to differentiate with the length of the string, right, in order to get the omega that you need. And the omega is equal to g. The omega squared is going to be equal to that over that. Okay, I remember the derivation for this. Omega is 2 pi over t as well. Alright, but you guys should be able to do this, man. You guys don't require the derivation for this, but everything should be good. But all you need for derivation is the fact that the tangential force is equal to the negative weight times sine omega. Well, not sine omega, sine theta. But you can get it from circular motion. Alright, it's not too much into this topic, right? But it's circular motion where we get these equations from. Alrighty? So those are just equations for the period and the frequency and relationships between the two. And with that, we have completed all the fundamental quantities that we need to describe simple harmonic motion. Therefore, it only gets more complex from here. Only. This is just the basics. Right? This is just the maths behind it. And we should be able now to use these things to describe other things. Alright? Okay. Can move on. We have to describe diagrams, right, as it relates to these things. No, they're not showing live. No. I mean, I may think of that in the future. All right, but let's look at this, right? So we're looking at this. These are two waves specific. Well, there should be 3 waves actually. So the next slide will have the 3rd wave, right? But we're looking at the different diagrams, right? So the first one we're looking at is the we have to discuss the displacement, right, versus the time. So the very first wave that we're looking at the top is displacement time graph for the sinusoidal oscillation, right? So we end up with this, right? And we have the amplitude here, the max displacement being the difference between the wave itself, where the wave is, right, and the equilibrium point. Right? Remember, the equilibrium point is 0, where x is equal to 0. So this is the amplitude here. And we see that the period now will be the time taken here. So remember, this is the displacement. So displacement there, time graph. Therefore, some persons may mix it up on the exam and say, okay, this is the wavelength. No, it isn't. This is the period, because this is the displacement time graph, right? A displacement time graph. So it's not the wavelength. It is the period t, right? So if we take identical sine curves now, right, and look at now the velocity now, the velocity is different, right? Remember, I want you guys to look closely here, and I need you guys to answer as I go through this, so I know that you understand or you're going with me, right? I circled the 0 point on the displacement time curve. We can see that, right? Can we understand that, right? So if we're looking at that now, that is when the displacement is 0. But remember the relationship between the quantities. If displacement is zero, then what? Velocity is max, right? Therefore, if we look at the velocity time curve now, wherever this displacement was zero, the velocity is maximum. Because at max displacement, velocity is zero now. So where this max displacement was up here, here the x max, now the velocity is zero. So we can now see the relationship between these things. Alright? It is important to understand the relationship between these things. I think it was Christine who had done a past paper yesterday, and they were asking her to draw these graphs. You must be able to produce these graphs. Alright? And you must be able to explain them, because you can't draw a graph and don't know how to explain it. Doesn't make any sense. Alright? So we have that there. The last thing now, right? We will be looking at this acceleration time graph now, where it is 90 degrees out of phase with the displacement, right? So remember the acceleration. What is the equation for the acceleration? The acceleration, right? Remember that we start off with a sine curve, right? Sine. Start off with sine. Remember, sine starts through the origin, right? Sine started through the origin here, right? But when we differentiate sine, it becomes cosine, right? That's why this curve for the velocity started up here, because cosine curves start at the max and not at the origin. That is what we're seeing here. We're seeing the math in the actual wave, right? If we were to differentiate again, the derivative of cosine is sine. We return now to starting at the origin when we speak about the acceleration time curve. And it will be negative, right? Here. Alright, so we're looking at that here. So the acceleration is the rate of change of velocity. So we have differentiated the velocity to return to this curve. And yes, if you do this in math class, you will end up with the same thing, because math is just a language of physics. Math and physics are not the same thing, of course. But that is what we work with. So it becomes a cosine curve. So when you're drawing these graphs, please note that these must be drawn in these specific ways, right? Hopefully I've gone through the explanations properly. Alright, so the acceleration time curve is like this. Of course, if you're sketching the graph, you won't have to put any values on it. You just sketch the curve how it's supposed to look, put in your x-axis to be what, and your y-axis to be what. Remember that the acceleration is identical to the displacement, but it's a reflection of the displacement, right? So where the displacement looks like, the displacement would have looked like, let's say, this. It would have been a reflection, right? So if you remember that, okay, I know how to draw my displacement graph, right? For my velocity graph, I don't start at the origin, right? I start at the max amplitude. And for my acceleration graph, I reflect my displacement graph. That is what I remembered in order to draw these graphs, you know. I just know my displacement, and I know what's supposed to happen for the rest. I reflect for my acceleration, and I start at the amplitude for my velocity graph. And I'm pretty sure you guys will just be asked to just sketch them. So it should be fine. Okay, the explanation is not necessarily explaining why each graph starts at what point. No, you can. But the explanation for, I don't think you'll be asked to explain the graphs really, but you should be able to look at the concepts and explain what's happening with it. So, you know, how do you define the, like, what is the period on the displacement graph here, and then okay, when the v is equal to 0, y is, you know, the displacement max on the displacement max curve. You just basically need to know how to draw the curve, so the waves, right, and understand the waves, right? So it's not that, okay, there's an explanation that you need to write down and know. It's not that. You just need to understand the waves. Once you understand it, you can answer any question. All right? Once you understand. That's another important thing to get across again, right? I don't want to explain concepts only because it appears in past papers, but for you to understand it is the reason why I'm here. If you wanted to pass the exam, I just do all the past papers, all the paper twos, all the paper ones, and post them, and then that's it. Don't need anything else. That's what you need to pass the exam, but understanding is more important. Alright, so just need to understand the wave, and then after that, you can figure out any other question that they're gonna give you about it. Alrighty? So we spent an awful amount of time here, and we get into springs now. A part of the syllabus now asks us to explain now. The student must be able to understand and to manipulate equations of springs in series and springs in parallel. That is where we will go after. Alrighty? So let's take a break here.